So this is the first example of a titration involving a strong acid and a strong base. And skip a number of lines down and draw this graph, and then there'll be lots of writing below this, and we'll come back to and refer to this graph as we go through the steps. So pH on the vertical axis, milliliters of titrant on the horizontal axis, and this assumes that we're going to have our acid, strong acid, in the beaker, and then we'll be adding a base from the burette, and we'll add it dropwise or a little bit at a time while we monitor the pH with a pH meter, and we'll record that milliliter by milliliter as we add the NaOH to the acid inside the container. So the first thing that you want to do is you want to write down the reaction. And the strong acid we're going to use is hydrochloric acid, and the strong base we're going to use is NaOH, and then this is going to produce water and then a salt, NaCl. Make amount on the left hand side over here below the HCl, so 50 milliliters of 0.1 molar. Then we're going to add NaOH to it little bit by little bit, and then we're going to make a salt that's not going to affect the pH in this case because it's from a strong base and from a strong acid, and then we're going to produce water as well that's not going to affect the pH as well. So we're going to calculate the pH as we're adding this at 4 different points. First of all, we're going to calculate the pH before we add any NaOH, so at the beginning. After we've added 49 milliliters of NaOH, once we've added 50 milliliters of NaOH, and then lastly, after we've added 51 milliliters of NaOH, after we've gone just a little bit past the equivalence point. So, step number A right here, before we add any NaOH, what is the pH in this beaker? So we know we have 0.1 molar HCl, and HCl of course completely dissociates, so we have 0.1 molar of the H plus ion concentration, and therefore the pH is equal to the negative log of that H plus ions concentration, and since it's 0.1, it turns out to be a pH of 1. And so at the very beginning right here, at a pH of 1, we'll put our first point right here. I'll just sketch this in here, and we'll get some other points here on the pH scale. And a pH of 1 is where we're starting when we've added 0 milliliters of NaOH. So secondly, we're going to take a look at just the net ionic equation now, because these are the things that are going to affect the pH as we go along. And we're going to make a big ice table here on the left-hand side and skip at least 3 lines between the I, the C, and the E, so you've got plenty of room to write this down. Now, when you do an ice table for titrations, you always have to be in moles. Always have to be in moles. You always have to be in moles. And we can use the molarity triangle here with the milliliters and the molarity to find our number of moles of H plus. And so we take 50 milliliters, we'll convert that to liters, which would be 3 to the left, 1, 2, 3, 0.050 liters, and then we'll multiply that by the molarity, or 0.1, and then we end up with 0.005 moles of H plus. Now we're adding 49 milliliters of NaOH, so we'd do the same thing, 0.049 liters times 0.1 molar, and we'd end up with 0.0049 amount of OH minus initially, when we have 49 milliliters of NaOH and 50 milliliters of H plus. Water, of course, isn't going to make any difference in when we're calculating our pH. So when this reaction happens, we'll lose the smaller amount. So the smaller amount is 0.0049, so both of these will lose 0.0049 when they react with one another. And then in the end, we'll just do a subtraction. And of course, this one will end up being 0, and this one ends up being 0.0001 moles of H plus remaining. The reason we wanted to be in moles is so that we can compare the amounts of each of these, and then when we add the volumes of each, we have 50 plus 49, or 99 milliliters inside of our container, and now we can find the H plus ion concentration by taking our moles and dividing it by the total number of liters. It's got to be 50 plus 49 because the beaker here now contains not 50 milliliters but 99 milliliters because we added 49 milliliters of base. So when we divide that we end up with 1 times 10 to the negative third molar. This is our H plus ion concentration. Take the negative log of 1 times 10 to the negative 3, and I end up with 3 for my pH. So from 1 milliliter away from the equivalence point, the pH is 3. So following along here, let's go way over here and say this is 49. We'll make this be 50, this be 51, and my pH went all the way up from 1 to 3. Oh, that's not very much. At 49, it went from 1 to 3 right here. Now let's calculate what it's going to be at the equivalence point, or at 50 milliliters, when the moles of acid are equal to the moles of base. So at this particular point, we have 50 milliliters of HCl and 50 milliliters of NaOH. And at this time, we could do the molarity triangle and find out that the moles of the acid are now equal to the moles of the base. And this is called the equivalence point, or the equal point between the acid and the base. But let's find out the pH at this point. So first, let's write our net ionic equation, or just our complete ionic equation here. HCl, NaOH, NaCl, and some HOH. And then convert to moles. So when we convert to moles right here, we're going to get the same number of moles here as here. And if you want to see that, remember in the molarity triangle, moles would be equal to the molarity times the liters. So my moles would be equal to 0.1 molar times my milliliters, or 0.050 liters. And so this would be 0.005. And then that would be the same for the NaOH. So they have the same amounts right here. And so when you subtract them, there'll be none of this left and none of this left. And of course, NaCl is not going to have any effect on the pH. So the only thing that's left is the H2O. H2O at 25 degrees Celsius, of course, has a pH equal to 7. And so at 50 milliliters, from 49 to 50, it jumps all the way up to here. So notice that huge rise in pH in just 1 milliliter difference of titrant added. All right, the last one we'll look at is 51 milliliters. 51 milliliters of titrant added. And so in letter D now, we'll just look at the net ionic equation again, because we really want to know what either one of these is to determine what the pH is. And so on the left-hand side again, make a big, long ice table and skip a couple lines in between each one. And once again, we have to go to moles for the acid, for moles for the base, to determine how many moles are going to be left over. Remember, in a titration, you always use moles in the ice table. So 50 milliliters, 0.1 molar, 0.005 moles. 51 milliliters now, 0.1 molar, 0.0051 moles here. So which one's smaller? The 0.005, so that one gets completely used up. It's subtracted from the OH minus. We end up with no acid remaining, but we have 0.001 of the base remaining, OH minus. And so now we could use this to find our concentration of OH minus in the solution. Remember, this is moles, and so I need to take my moles and divide it by my milliliters. And I have 50 milliliters plus 51 milliliters, or a total of 101, or 0.101 liters. Divide those two, and I end up with 1 times 10 to the negative third molar of the OH minus. So from this, I can find the pOH by taking the negative log of 1 times 10 to the negative third. That gives me a pOH of 3. I want to know the pH to graph it up here, so subtract that from 14. 14 minus 3 means my pH has now, in 1 more milliliter, jumped from 7 all the way up to 11. So from here to here, I've gone way up this height right here, so that gives me a really steep part. And then if I did a little bit further, it would actually level off up here, and that's what gives me that steep S-shaped graph. So after 1 milliliter, after meeting the equivalence point, the pH has jumped between 49 and 51, from 3 all the way up to 11. This is caused, of course, because we're right at the equivalence point, and it's driven by either a little bit of strong acid or a little bit of strong base remaining at the end of the titration. So throughout this video cast, I hope you learned you should ice table when you do titrations, And you should do it in moles, always in moles. And then after you've done that, find the concentration and take the negative log of the leftover concentration. Don't forget to divide by the total number of liters that are in there. Next, we'll take a look at a weak acid and strong base titration. It is the toughest, longest problem of all time. Good luck with your titrations.